So the 2012 paper, question 6, Simple Harmonic Gravity, is scholarship physics in case you don't know. We've got some information at the start, and then we have to imagine a hole is drilled from the South Pole through the centre of the Earth to the North Pole, and we're looking at simple harmonic motion of an object that falls from the North Pole down towards the South Pole, and then gravity draws it back again, and it goes back and forth. And by using Newton's Law of Gravitation, we have to show for uniform internal density ρ, which is given above, that the hole will, an object dropped into the hole will perform simple harmonic motion. We've got a hint there which is very helpful. We can consider any mass that is outside the immediate radius, any mass that is outside that particular radius, we can ignore it. So we don't need to take that into our calculations, anything outside of that mass. So anyway, to show that something is simple harmonic motion, we have to show that the force or the acceleration is proportional to the negative of the displacement, or in this case r, our radius. So Newton's Law of Gravitation, Fg equals g mass of the Earth times the mass of the object divided by the radius that you happen to be at squared. And we can simplify this. We can just go to the acceleration, because the force and the acceleration are proportional. So we can just go to the acceleration equals, and I'm also doing that because later on it's useful in the question, equals the universal gravitational constant times m divided by the radius squared. Now, we've got a problem because it looks like the acceleration is proportional to the inverse of the radius squared. But we can deal with this mass. The mass of the Earth is equal to the volume of the Earth at a particular radius times the mean density, which is the mass per volume. So we can then take this as 4/3, because we're dealing with a sphere, pi radius of the Earth cubed, and times by the density. Well, I shouldn't write p, it should be rho. Anyway, substitute that in, and you end up with A equals g 4/3 pi r cubed rho, I did it as a p again, my bad, and r squared. So you can see now r squared is going to cancel out with the cubed, and we're left with just r to the power of 1, and that means the acceleration here is proportional to the radius. And the negative is just a trick of vectors. So the radius is measured from outwards, the further out from the centre you go, and the force of gravity is downwards towards the centre. That's where the negative comes from. So that shows from this equation, and you would have to write something to that effect, that from this equation it's clear that it will undergo simple harmonic motion. Next bit, calculate the period for this simple harmonic motion. And I might just go back to my blue pen because I prefer that. The period equals 1 over the frequency, or if we're dealing with simple harmonic motion, it might be better to use our omega equals 2 pi f, our angular frequency. So we'd rearrange that to get the period as 2 pi over the angular frequency. And we also have, so we're going for simultaneous equations here, so there's one, if you ignore the f bit in the middle. So we're only interested in t equals 2 pi over omega. And we also have from the maximum acceleration equals omega squared a, we can rearrange and get another equation of omega equals square root of the maximum acceleration times the maximum displacement, or the amplitude of motion, or in this case the maximum radius. Excuse me. So we can further detail, maybe it's helpful to write these so you can, so the maximum acceleration equals omega squared a, and that's what we got this part from, and from up the top it was omega equals 2 pi f, or 2 pi over the period. Anyway, so it's our second equation. We can detail our second equation just a little bit more. From our earlier bit above here, we can see that the acceleration, in fact the maximum acceleration, is going to be g times 4/3 pi r max, has to be r max, times the mean density, and we'll end up with Amax, where are we? I'm just gonna combine these two down here. Is going to be omega equal, I might have to move across, I am trying to rush because I've got a bell coming soon. So omega equals 4/3 g, slight rearrangement of the letters, pi rho, r, or r max if you like, and that's going to be over r max, and all of that is square rooted. So a max we've just substituted in up the top there, but we've called a max rather than just a, and r max rather than just r, because for the maximum acceleration we need the maximum radius, which makes sense because that's the furthest away from the equilibrium position in the centre of the Earth. And for a, the maximum amplitude is the maximum radius. So anyway, that gives us an equation. We can then cancel out our r max, because r max would be the radius of the Earth. We could use that if we wanted, or we could just cancel it out, which is easier. And then we're left with rho, which we know, pi, which we know, g, which we know, and 4/3, which we know, and we can calculate omega. Once we know omega, coming back across here, we can substitute it into here, and we know 2 pi, so we can calculate t. Wonderful, isn't it? So you might like to rewind and watch that one again, just to follow it through, because it did go in a bit of a weird way. Okay, C. Explain in what way this period is related to the orbital period of satellites in low Earth orbits. Let's draw a diagram. Satellite in low Earth orbit, and let's just show on this diagram the period of the simple harmonic motion. It's there and back. Oh, this looks interesting. This looks like a reference circle. Reference circle for the low Earth orbit, LEO, low Earth orbit satellite motion, is equivalent to the reference circle for the simple harmonic motion. That's what that's all about. So you could also say the period, so that means the period is the same for the low Earth orbit and for the simple harmonic motion. You could prove that if you wanted by doing some calculations, because you have enough information to calculate the period of the low Earth orbit, and you would find that it comes to the same as the period in the previous question for the period of motion for the simple harmonic motion. So you could actually calculate it as well. Last part, D. D. Discuss the differences in the motion of the falling object that would be observed if the hole were drilled from an equatorial position rather than from the South Pole. So this time it's all to do with the spin of the Earth. The Earth is spinning about its axis. It's on a bit of a tilt, but we won't worry about that. And instead of the object being dropped along the axis down this way, it's being dropped this way, okay, or the other way. Doesn't matter where, but it's dropped from an equatorial position. So the big thing here is, which they're aiming for, there's actually a lot of things you could talk about, but I'm going to focus on just what the marking schedule focused on, and we're going to assume that you can assume those things prior to answering the question. So we're going to assume there's no friction or air resistance. I think we were told that earlier. But in this case we actually have to assume there is a bit of friction, because this object that you drop down the hole is going to bang against the sides of the hole, and we're going to explain that, attempt to explain that. So let's just assume that's not the North Pole and that's not the South Pole, but we're still spinning through, like around, maybe looking straight down as the pole. So the Earth is rotating on its axis that way, which is just another perspective for the same situation. So we've got an object being dropped and it's going through. At the initial point it has a maximum linear velocity at a tangent to the direction of the little surface of the Earth. Tangent to the surface of the Earth? Tangent to the radius. As you go further down the hole, each of those positions will have a smaller v until you get to the center, where it's effectively not rotating. But another way to think about this is halfway down the hole, to maintain the same angular frequency or angular velocity, you have a slower linear velocity at any point than further out. Okay, because you have to cover the same an angle of rotation in the same time, but your distance, your radial distance, is closer to the center, so there's actually less circumference of that circle to cover. So your linear velocity is less, so v is less the closer to the center you go. Now what that means is you're going to start off with a larger velocity, so you'd be moving faster in a linear direction than when you go down the hole. So when you go down the hole, you're still going to have this initially, but the Earth is only moving that fast. So that means you're going to bang into the side, and that's going to slow you down. So I guess friction doesn't matter, it's just a straight-on collision and a change in momentum, therefore a change in velocity. So you're going to bang into the side pretty much all the way down, and then I guess you probably would have stopped by the time you hit the center, because all of your momentum is lost going through there. So the only final thing is to say which side of the hole you will be crashing into, and it's going to be the east side, because the Earth is spinning towards the east. If you think the Sun is out here, and when the Sun sets, it sets in the west, that's because the Earth is spinning away towards the east, and the Sun disappears. Its relative motion would be that way, down the western horizon. But anyway, your initial velocity is towards the east, and the easterly velocity of those instantaneous points as it's passing down are decreasing, but your initial velocity is a larger east than those smaller east ones, so it's going to hit into the east side. And there you go.